We looked at how to graph rationals when they're in transformational forms, but there's a whole bunch of other rationals that are not in transformational form, but we still have a way that we can graph them. To remind you, our rationals are anything that can be written as a fraction, right? Those are our rational numbers. So when we have rational functions, it's really quotients of polynomial functions. So I have a polynomial function on top and a polynomial function on the bottom. So both p and q are polynomials, and I am dividing the two of them. Notice we have this specification that q of x cannot equal 0. That's because q of x is on the bottom, and remember, we don't divide by 0. Right, so we're saying we're looking at it as long as this part is not equal to 0. Okay? That also is what our domain restriction is, right? That's what we had been doing when we got our rationals in transformational form. We set the bottom equal to 0 and solved. Okay? So this, having a variable in the denominator, makes it so that there's going to be a domain restriction. Okay? So what you can do is you set, there's two ways you can look at it. You can set the denominator not equal to 0 and solve, and then that's what your domain restriction is, like x cannot be those things. Or you can set it equal to 0 and then negate it at the end. Either one is acceptable. They get you to the same spot. Now remember that if you have something that's quadratic, or any higher power than 1, in order to solve, you may have to factor it or use the quadratic formula. Typically, we don't give you ones that use the quadratic formula, but that's still a possibility. Okay? We've been working with asymptotes, but remember, asymptotes are where the graph approaches and gets really, really, really close to, and depending on what kind of asymptote is, it may or may not cross it. Okay? You never cross vertical asymptotes. So our vertical asymptote comes from a variable being in the denominator. So you set the denominator equal to 0, or like I just said, not equal to 0, and then solve. With your vertical asymptote and the domain restriction, your vertical asymptote is always written as x equals, and then your domain is x cannot be equal to whatever the numbers are. So when you solve the denominator. So if I have the domain, I have x cannot equal, but our vertical asymptote is x equals those two things, or those, it's two things usually with our rationals, but whatever sets the bottom equal to 0. Okay? The graph never crosses a vertical asymptote, not ever, ever, ever. Okay? We also have multiplicity, just like we've had before with our polynomials. So our multiplicity plays a part in our graph here. Okay? Remember, your multiplicity is determined by the power for each asymptote, so for each factor. Okay? We have even asymptotes and odd asymptotes. Okay? So if it's an even asymptote, the end behavior to the left and right of asymptote is the same. It's either up, up, or down, down. I'll give you a picture in just a second. And if it's an odd asymptote, they have opposite directions. So notice we have this vertical asymptote here. So as we're coming on the left side of this asymptote, we're coming from below, right? And then on the right side of this asymptote, we're coming up from the top, right? So we have the odd, notice it kind of looks like our discoing end behavior. They're coming from opposite ends, right? So this would be an odd asymptote. Here, if we look at this asymptote, this would be our vertical asymptote that we have. If we look on the left side, we're coming from below. On the right side, we're also coming from below. So on both sides of the asymptote, to the left and right, we're coming from the same direction, which means that this would be an even asymptote. So your odd asymptotes will, we've got an asymptote that looks like this, either be coming like this or like this, right? And then it'll go somewhere from there. And then your even asymptotes, you'll have your asymptote and they'll be coming from the same direction, which could either be down, down, or up, up. Okay? So that's your even and odd asymptotes. Okay? And that helps us determine where the graph is using that information. Okay? So if we want to look at our first example, we're stating the domain and the vertical asymptote. So these both come from, this one you set the denominator not equal to 0. This one you set the denominator equal to 0, and you solve. So typically I usually set it equal to 0 and then find the vertical asymptotes, and then I negate it for the domain. Again, you could set it not equal to 0 and be like, oh, that's the domain, and then negate it so that it's x equals, and then those are your vertical asymptotes. What I need you to know is that your vertical asymptotes are x equals and your domain is x cannot equal. Okay? So remember, the vertical asymptote comes from the bottom because we don't want that to equal 0, because if it equals 0, we're dividing by 0. So I set x squared minus 1 equal to 0. Well, this is quadratic because the highest power is 2. So that means I have to solve that. I can factor. This is a difference of squares, so this is x plus 1 and x minus 1. So we get x is negative 1 and positive 1. Or you could write it as x equals plus or minus 1. Both are acceptable. Okay? The other way you could look at it is that you add 1 to the other side, and then you take the square root. When you take the square root, you have to do plus or minus, so you get x is plus or minus 1. Okay? Both of those get you to the same spot. Their multiplicity comes from the factor and the power of the factor, just like we did with our polynomials. So the multiplicity of each one of these is 1, right? Or if you're doing this one, they showed up once, so the multiplicity would be 1, right? Which means that it's going to be an odd asymptote. Okay? And then that's all we're doing at the moment. Right? We'll get to the part where we're putting it on the graph, but that's all we're doing for the time being. Okay? Now here we have this. If I want, so let's go back. So these are the vertical asymptotes. And then our domain is x cannot be plus or minus 1. If you're going to write that in interval notation, you would have negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Right? So there's this gap at negative 1 and this gap at 1, which is what this says. There's a gap here at positive 1 and negative 1. Okay? It's quicker to write it where you're just saying x cannot equals. So the interval notation is something that usually we forego doing in this just because it's tedious. We don't love tedious things as mathematicians. Okay? So those are our vertical asymptotes and then our domain. If we look at the second one, we have, I want to set the denominator equal to 0 to find those. So 7x squared plus 19x minus 6 equals 0. And so I'm going to do 7 times negative 6, so I'm trying to multiply to negative 42 and add to 19, right? Remember, it's this number that goes here. And don't forget about your factoring. When it's a quantity squared, you need to set it equal to 0 to solve. So now I've got 1 and 42, 2 and 21, and then I'm going to stop because 2 and 21 can get me to what I need to have. Okay? So I have to pay back the 7. All right, so remember, I used that color already. The 7 has to go back on both of these. Then I look to see if there's a common factor with 7 and 2. There is none. I look to see if there's a common factor with 7 and 21. There is one. 7 goes into 7 once. 7 goes into 21 3 times. So, I forgot my signs also. Got distracted. To get to positive 19, I need the 21 to be not positive and the 2 to be negative. And then we have negative 2 times positive 21 gives us negative 42, but adds to the positive 19. So then we get 7x minus 2 times by x plus 3 equals 0. So then that means that we have x equals 2/7 and negative 3. Remember, our shortcut is change this sign, divide by this. Change this sign, divide by that. So negative 3 divided by 1 is negative 3. The multiplicity comes from the power, so both of these have an unset power of 1. So their multiplicity is 1, so that means that it's an odd asymptote, right? And then that's as far as we're going. So these are our vertical asymptotes, okay? And then our domain is x cannot equal those two things, so 2/7 and negative 3. Again, remember the vertical asymptotes are x equals, your domain is x cannot equal. So you could set this equal to or not equal to and then solve, and then remember that you have x equals for your vertical asymptotes and x cannot equal for your domain restriction. So if we look at this last one, notice I've ignored the top on all of these because when we are finding our domain and the vertical asymptotes, it comes from the denominator. So I'm not even caring about the tops. I just care about the bottoms right now. We'll get to the tops in a little bit, but we just care about the bottoms for our domain restriction and for our vertical asymptotes. So here, I'm multiplying 25 times the unsaid 1. So I want to multiply to 25, and then I'm adding to 10. So we've got 1 and 25 and 5 and 5. Those are our only options. 5 and 5, notice the signs are both positive because it multiplies to 25 but adds to a positive 10. So then this is really x plus 5 times x plus 5 equals 0. Or you can see it as this is really x plus 5 quantity squared equals 0. Right? Now remember when we solved these, if we take the square root of both sides, it's really plus or minus 0, but that doesn't impact 0 because 0 is neither positive nor negative. So then I just subtract the 5, so we get x is negative 5. Okay? If we solved it from here and we did x plus 5 equals 0 and x plus 5 equals 0, I would get x is negative 5 and negative 5. Right? So this is important because we want to know our multiplicity. So if we look here, notice we would have each one of these as a 1, but they showed up twice of the same number. So then that means that our multiplicity is 2. Or you can get it from the fact that the thing times by itself is really squared, which means that its multiplicity is 2. So again, your multiplicity either comes from the power or how many times it shows up, depending on how you're looking at it. Okay? So the multiplicity is 2, which means that this is an even asymptote. Okay? Again, we're not doing anything with that right now. We'll put that together in a little bit. So our vertical asymptote is x equals negative 5, well, the multiplicity of 2, and our domain is x cannot equal negative 5. So that's how we find our domain and vertical asymptotes when we have more complicated rationals that are not in transformational form.